Okay. So, sorry, it's a start. Yes, sorry about landowning. I don't know how that line got there. So today we move on to interacting systems. I have two quick comments on the non-interacting case, mostly to just save you some time if you're ever doing a practical calculation of either a Chern number or a Z2 invariant. If I had known these, it would have saved me some time. So I will tell you some tricks, two quick tricks. And then the main part is I want to go through the microscopics quickly of the fractional quantum Hall effect, choosing the simplest fractional quantum Hall state, the so-called Laughlin state, as the example. And I will use maybe a little bit from the tutorial. Basically, I'm just going to use this basis for the lowest Landau level. That's about the only thing I need to use, which I think Titus just covered in the tutorial. But from that, we will write down a model interaction and a model state, and I will try to convince you that this is a reasonably physical state with some incredible properties, and that will motivate some of the later stuff we do on Friday. But between now and Friday, I thought it would be nice to maybe make a connection between some of the stuff that I'm covering and some of the things you've heard in other lectures. So, for example, you've heard a couple of facts about spin chains from John Chalker and Nicolas Regnault. And as our warm-up on topological field theory, I want to explain mostly a famous argument from Haldane in the early 80s, even before AKLT, that's really about why spin half chains are very different from integer spin chains in one dimension. That's basically for a topological reason. It's because of a Berry phase. So it'll help us practice Berry phase, do a little bit of topology, and then when we think about the spin 1 chain and slightly more complicated parameter values than AKLT, we need to use a little bit more of our topological knowledge to deal with something called Wess-Zumino-Witten models. So I'll go through that. Maybe you can read more if you like, but for us it'll be a nice way to use some of our topology that we've learned in the first lecture. And then I don't think I will get very far on this today, but on Friday the main subject is going to be not just a topological term that we add to a standard field theory, but a fully topological field theory, so-called Chern-Simons theory. And that is one of the more beautiful things. Chern-Simons theory was a large part of Edward Witten's Fields medal, for example. Leaving aside its contributions to mathematics, it sort of unifies what we understand about the quantum Hall effect, both integer and fractional, in the same way that Ginzburg-Landau theory unifies what we know about symmetry breaking. So I think just as an accomplishment, it's very important intellectually, and it even predicts a few things about experiment. So these digressions into field theory I will try to make as accessible as possible, and one nice thing about both these examples, which one should admit is not always true about field theory calculations, is that they made specific predictions about experiment that were actually verified that people weren't able to make, at least they weren't able to make beforehand by any other method. Okay, so the two comments on practical calculation of Z2 and integer invariance was calculating Z2. I gave you this Chern-Simons integral over the band structure, but it's actually much easier if we have inversion symmetry. That is, if the material, which is often the case. And I'm not going to show this formula. I mean, I'm going to write the formula, but I'm not going to try to derive it. Deriving it is not easy. It's around 2007, I think. So we know that time reversal takes k go to minus k. Call the points in the Brillouin zone with k equal to minus k. T, R, I, M trims, which is time reversal invariant momenta. So in our original Foucault argument, we thought about 1D, and we said that 0 and k at the edge of the Brillouin zone are the two time reversal invariant momenta in 1D. If I took the square in 2D, then there are 4 inequivalent trims. And in 3D, there would be 8. And the formula, well, there is no Z2 invariant of this type in 1D, but in 2D and 3D, if we take the product over trims of a quantity which is the I want to take the product of the parity eigenvalues, let me write it this way. So I have an inversion operator, and there's a way to analyze these time reversal invariant momenta under the operation of inversion, which also takes k to minus k, and label them as either inversion even or inversion odd. And so in other words, I can give a number plus or minus 1 to each of these. That number plus or minus 1 is what I mean by minus 1 to the parity. And if I take the product, so in other words, it's like saying that there's a Z2 invariant at each one of these points. Now, those are not all physical. There's some gauge dependence in how you assign the action of parity, but the bright side is that the product of the 4 is invariant, and in 3D, the product of the 8 is invariant on what choice I make to define the inversion operator. So I'm not giving you the details of the trick, but if you ever have to compute a Z2 invariant for some nice 2D or 3D band structure you've written down, if it has inversion, this is what you should do. So you should go look at their paper. Yes?
So do we have to fix the gauge? Because you said
you should fix a gauge to compute this, but different gauges will give you the same answer. I mean, I'd say you should fix an action of the inversion. I mean, in general, actually that gets to point 2, which is for Z invariance. There, the way I gave you so far, so as far as I know, you do have to fix a gauge for Z2 invariance. For Z invariance, what I've told you so far would be to compute things like A, which is I psi k, grad k, actually I called it UK. So I would have to pick some wave functions to compute the vector potential. I would then compute curl of A, which is F. So one option, which is kind of brute force, is to just make sure that in every little patch you have a well-defined A. We know that if the integral of F is non-zero, there's no global smooth choice of wave functions, but I can choose them in a little disk, compute F in that little disk, and then F is gauge invariant, so I just add up F. But there's a useful formula, which is how to write the Berry curvature entirely in terms of something gauge invariant. So in other words, you can do this, but it's a little messy and slow, and you have to be careful to make sure that your wave functions are being chosen smoothly by whatever computer diagonalization you're doing, because we had to introduce something gauge dependent, the wave function, in order to compute something F that's gauge independent. So why don't we just find a gauge independent way to compute F? That's not possible for all the topological quantities I know, but it is possible for F, which is in terms of the projection operator. So let's focus on the case of one band to start with. This is the projection operator that takes any state which is proportional to UK, independent of its phase, gets taken back to itself, and any state orthogonal to UK gets taken to 0. So it's called a projection. It's basically projection onto the subspace spanned by UK. But if instead I took e to the I phi times UK, so if I took a different phase, it would cancel out in the projection. Similarly, if I wanted to project onto 2 or 3 bands, I would take P as sum over whatever bands I want, let's say all the occupied bands of U sub kj, U sub kj. Then F is the following. It's the trace of partial xp, so that P is some matrix. Partial x, I mean partial kx, to be precise. multiplying p, multiplying partial yp minus x goes to y. And if you don't believe me, you can stick, this one you can actually do algebraically with a little bit of time, which you can't really do with that. If you take this and just plug it in and figure out which terms survive, you can kind of see that I've got, kx and ky derivatives. And those derivatives, once I swap them, will give me something that starts to look like f. In fact, it is exactly f. And if I do it, the point of the trace is if I do it for multiple bands, then I will get the sum of the Chern numbers for all the bands up. So in particular, where this is especially handy is if you might have bands becoming degenerate or something like that. Here you just project onto all the bands that you care about, and any degeneracy or anything like that, the projection operator onto the subspace spanned by all those bands is still smooth. So those are kind of technical comments that don't really have a lot of physics in them. I still thought they would be useful because, who knows, some of you might wind up computing something like this. Now we can get back to physics. So that was my quick remark. Oh, 2 questions.
Oh, and actually, I think a similar construction works for the Z2 invariant also. Like with Wilson extension.
I guess I have seen efforts on that, but at least for the 3D one, I don't think without inversion that there is a... Maybe we could talk later. Maybe you can...
Bernavik has a paper on it. Yeah.
I'm aware that Bernavik has a paper on it, yes.
I think that's a reference for
The projection operator trick. Yes, that is in Avron, Seiler, Simon, 1983. PRL. Okay, so enough technical detail. Let's do some classic physics that I guess had its 30th birthday recently, the Laughlin theory of the fractional quantum Hall effect. And the easiest thing to do is to start with the integer Hall effect and make one seemingly trivial change. So the integer Hall effect, we know that we get a nu equal to 1 quantum Hall state by filling up the lowest Landau level. So everything I'm going to say is lowest Landau level. We know that the lowest Landau level has a basis in the rotational gauge, which are these wave functions. And this just means I'm not going to write the normalization. Okay, so in other words, they're of the form some polynomial in Z, where Z, again, is x plus iy, and something to keep the electrons from flying off to infinity. And these you can view, I even kept Tius's writing, so that's why it's neater. You can see that these are rings basically peaked at this radius, which increases as m increases. M is basically the angular momentum, because I've got x plus iy to the m. So it's like LZ. Actually, yeah. So, okay. L is the magnetic length. This is 2 pi L squared is h over e. Okay, so the nu equal to 1 state, and let's write the one closest to the origin. Well, if I'm going to write that in terms of all the electrons, that's going to be a Slater determinant of the states psi m, with m running from 0 up to n minus 1, where n is the number of electrons. Okay, so with that set, actually, there may be one quick comment. For the... Okay, never mind. Okay, so with this set of wave functions, sorry, I was going to say something, but I took it back. Let's figure out a way to write that that's more elegant. We can write it as... Hopefully you copied that down by now. Product. So I'm going to write my many-body wave function. This is first quantization of z1 ... zn as product over I less than j of zi minus zj to the power e to the minus sum over I, zi squared over 4l squared. So this is the normalization factor for all the electrons. That's going to be there. And then here, well, we've made something that is anti-symmetric if I exchange any pair of I and j. So that's good. Let's check what is the degree of this polynomial. So in general, the way this basis of states works, if we calculate the degree of a polynomial, that is the powers of z that appear, that's related to how far is the wave function spread out from the origin because of this connection between m and mean radius. So here, okay, well, for every pair, counting once, we've got 1 power. So we should have n times n minus 1 over 2. So that's 1 power of some z sub I for each pair. And the number of pairs of n objects is n minus 1 over 2. But this is also the sum 0 plus 1 plus 2 plus 3 plus ... plus n minus 1, which is the angular momentum if we remember that we wanted to put 1 electron in the m equal to 0 state, 1 electron in the m equal to 1 state, 1 electron in m equal to 2, ... Okay, so let's now, so this is an argument that these are actually, this, when I say Slater determinant, this is just a way of writing the Slater determinant of my n electrons. So now, this state, we could justify in terms of non-interacting physics. If I thought about putting my system in a bowl, let's say V of r going as some number times r squared, something to kind of keep the electrons in the center, then I can imagine that, say, for reasonably small alpha, this will be the ground state. Okay, just on independent electron considerations. This is the most compact way of putting n electrons in the lowest Landau level. So now, let's add one new thing. Let's put a 3 here. So that's the famous Laughlin state. It doesn't seem like a huge change, really, but turns out that 3, or in general, let me call this m. So in this slight abusive notation, there's also that m. Forget about that m for now. This is going to be some odd number because I want to have statistics. So if I don't say further details, the case I'm mostly going to focus on is m equal to 3, which is one of the strong fractional quantum Hall plateaus in experiment. But the same argument sort of works for any odd m. M equal to 1 is the integer quantum Hall state. Okay, so what does that do? Well, that changes the degree now to 3 times n minus 1. So it's no longer a Slater determinant in quite this way. The way to think about it, and I'm going to come back and give you an argument why this is a good wave function. So if someone gives you a wave function, you should maybe ask at least 2 questions. One is, what are the properties of this wave function that are sort of generic, that I expect to be true, even if this wave function is not the exact wave function? So for example, the BCS wave function is not actually the wave function of any superconductor. It's a good model. What is the sense in which this is a good model? And then the second question you might ask is, well, why on earth would this be the ground state? And I'll give you an argument due to Haldane for why this should be the ground state. At least why it should be close to the ground state. Okay, so what this means, well, if I've increased the degree by 3, before, which was m equal to 1, every angular momentum state was occupied out to n minus 1. Now, on average, it must be that only 1 in every 3 is occupied. So you could think of it, if you want to draw a little box for m equal to 0, m equal to 1, 2, 3, 4. On average, 1 in every 3 boxes is filled. So you might draw something like this, except that somewhat detailed numerical calculations confirm that the Laughlin state is actually a liquid. So really you should think more about fluctuations, but with an average density of 1/3. And that is enough to explain why the fractional quantum Hall effect, sigma xy equal to e²/3h, is seen in an experiment. Because if you remember, the Laughlin argument I gave before was that pumping a flux basically moves this into that, and so on. It's kind of like a conveyor belt that shifts everything a little bit outward. Well, now, if the average density is 1/3 instead of 1, then inserting one flux, well, that's shifted everything to the right one box, but that means, at least on average, we should maybe check that it's precisely 1/3, but on average, charge E/3 is transported by one flux quantum. The last thing I say about the Laughlin state will be to try to convince you that there's reality to this fractional charge E/3. I can write a very simple excitation of that wave function that has charge E/3. Or maybe, if E is the electron, has charge minus E/3. It's a quasi-hole. Before we do that, maybe the biggest question about this wave function, though, is you might think if I fill up 1/3 of a Landau level, if I did that with no interactions, that would be a gapless state, because there would be many different arrangements of the particles in the boxes. This Laughlin state is not only a liquid, it's an incompressible liquid, meaning simply that it has a gap. So I want to argue why this is the ground state, and at the same time argue that it has a gap. So the precise argument that Haldane gave is called a parent Hamiltonian argument. It's basically like, rather than show that this is close to the ground state of the real Hamiltonian, let's show that it's the exact ground state of a Hamiltonian that might be close to the real Hamiltonian. So, pseudopotentials and parent Hamiltonian. Turns out that Haldane is kind of the hero of this lecture. That's accidental. I guess he happened to do two nice things that are both topological. So here we go. What do pseudopotentials mean? Well, the reason why you might guess that this is a reasonable wave function for the interacting case is that it keeps the electrons apart even better than Pauli exclusion requires them to be apart. So Pauli exclusion means that the wave function has to vanish when I put two electrons on the same site. This is saying it vanishes even more rapidly than just one power. It vanishes as 3 powers. So maybe there's some reason why interactions keep the electrons apart in this particular way. The idea of pseudopotentials is that any two-body interaction and let me assume that it's just depending on the magnitude of the distance between R1 and R2, is very simple within the lowest Landau level. It's fully determined, or its action within the lowest Landau level, I want to argue, is determined by a list of numbers V1, well, in principle, V1, V2, ... Some of these are 0, or some of these don't even matter because electrons are fermions. But the main point is I don't actually need a full functional dependence. I just need some numbers. Let me argue why that's true. So in general, you'd say, okay, well, even within the lowest Landau level, which has this discrete basis of angular momentum, I should have an interaction that looks like V ij, KL, let's put it that way, that takes electrons that were in I and J to K and L. So this would be if you gave me any two-body interaction, I could expand it in my angular momentum basis states like that. But the key now is to think about, first of all, angular momentum is conserved by this interaction. So we would expect, number one, angular momentum conservation. And if you put that in the right way, it's surprisingly powerful. So the basic idea of this, and actually for everything I'm saying, the book I mentioned before by Prengi and Gervin has chapters by Laughlin and Haldane that go into more detail. But the idea is, let me think about a better basis for two particles in the lowest Landau level. So construct Z1 minus Z2 to, let's call this little l, Z1 plus Z2 to the big L. So you could think of this as relative angular momentum. And this one is center of mass angular momentum. And let me make a plausibility argument for why what Haldane said is correct, which is center of mass angular momentum is basically taking the two electrons and moving them together around the origin. And the interaction is not going to care about that because the interaction only cares about the distance between them. So that's an argument that the interaction is, first of all, well, if it conserves total angular momentum and it doesn't care about center of mass angular momentum, then it's going to conserve that as well. So the interaction is actually diagonal in the L, L basis. And the second thing is, well, if I've got two particles and I move them around together, the interaction isn't going to care about how they're moving around together, so the magnitude of the interaction is only going to depend on little l. Yes?
Isn't that equivalent to say that the interaction is the centrosymmetric interaction?
Yeah, I wrote down a centrosymmetric. Yeah, so any centrosymmetric interaction, this is true. That's right. The only point is we're in the lowest Landau level, so it's a discrete basis. But yeah, once I say it's a discrete basis of the lowest Landau level, any centrosymmetric interaction will have this property that if you tell me how the interaction depends on the relative angular momentum, I'm done. The only remaining part of the work is to do some complicated basis change from my original basis to this basis. Or let's say I know the interactions in this basis, so I transform back here, and that gives me Vijkl, and I can't write those out in a very simple form, but I know that they all have to come from one set of numbers, which you can think of as V sub L. So the interaction strength between two particles of relative angular momentum L. And yes, it only depends on the centrosymmetry, so this is true for Coulomb or whatever. And that's what motivates the next thing Haldane did, which is cook up an artificial interaction that the Laughlin state likes, because if I look at what are these interaction coefficients for the Coulomb case, they're never zero. They fall off slowly with L. So if I plot V sub L versus L, this would be the real world, the Coulomb interaction. And as it turns out, we only care about odd L for fermions. So Haldane's idea was, well, what's special about the Laughlin state? The Laughlin state is the lowest degree polynomial such that every pair of electrons have relative angular momentum at least 3. So that's Haldane's picture of why Laughlin's wave function is the right one. Because of the following, that means that V1 could be very large. as long as V3 is 0 and V5 is 0 and so on. So that's the artificial interaction. If you Fourier transform that back to real space, you get the kind of thing that would make a mathematician vomit. So just think about it in terms of the pseudopotentials, because we're physicists. It's not self-adjoint or something. Fine, whatever. We're physicists, so it's okay. Then this interaction can be very strong. There can be strong repulsion in the L equal to 1 channel as long as the L equal to 3, 5, 7, etc. channels are weak, then the Laughlin state is exact. So to be precise, let's imagine doing a diagonalization. This is what I did at one point for a thesis project. Suppose I took that Haldane interaction and diagonalized n interacting electrons in LLL. This was back when computers were not so large, so I think n was 6 at most. Now maybe you can do a few more. So let me plot versus total angular momentum what the energy looks like. So there will be states like the integer quantum Hall state. Well, that'll actually be the first state that appears. So that will be at n minus 1 by 2. But if V1 is large, then the integer quantum Hall state will have a lot of energy. So it'll be up here somewhere. There'll be a lot of other states that come along, da-da-da-da-da-da-da. But then there's a point where I get a nice value of the energy, which is 0. And that is 3 n minus 1 by 2. That's the Laughlin state. And then you will get copies of this at higher angular momentum. In fact, every time you have a state, to be strict, you should keep drawing copies of it, because I can always increase the center of mass angular momentum of the state, and it will have the same energy. That's true until I add my confining potential. Once I add back the thing I erased, if I add a little bit of this, then at least you can see how in first-order perturbation theory, since radius increases with angular momentum, that will just kind of curve things up. So you'll get stuff that goes up like that. I'm sure you'll see plots, if you haven't already, of the detailed counting here. I guess 1, 1, 2, 3, 5, something like that. But the point is that this is the absolute ground state if I put in a confining potential. And this pattern here of edge excitations, this is that gapless edge. And in fact, this pattern is exactly the same pattern that appears for the edge excitations of the integer quantum Hall effect. So a question you might keep in the back of your mind, if the fractional quantum Hall effect is more interesting than the integer quantum Hall effect, which it probably is, why does the edge look the same? And the answer is that the edge is quite different. That's a prediction of the field theory that we do next time. Even though it looks similar in exact diagonalization, if you think about how an electron acts on the edge, it's very different. And that's seen in experiment. So that's what the edge state looks like in a calculation of a finite system. Let me, to close, show you one more neat property of this wave function. So there are maybe 3 properties that it would be nice to show you. 2 of them are not as easy without maybe sending you to do the calculation or forcing you to believe some things without any good argument. But 3 things you could get from this wave function are fractional charge. So that I will do. In a sec. Fractional statistics. I will define that as the last thing I say about fractional quantum Hall today and try to convince you that it might exist. It exists specifically because we're in 2 dimensions. There is no fractional statistics of point particles in 3D. You would need to have line-like particles or something like that. But in 2D, the stuff you learned about there being only bosons and fermions is actually wrong. It was known in principle that it could be wrong since 1976, work of Linus and Merheim, and I'll kind of sketch their argument. No one had any idea that might be physical. I mean, as far as I know, no one had any idea that might be physical until Laughlin wrote down this wave function. And then the last case, which you've already heard about from Xiaogang at least, is ground state degeneracy. So that is to say, instead of doing the calculation on the disk, you could do it on the sphere, which doesn't have an edge, and you could do it on the torus. And if you do that, you find one ground state on the sphere. If it's a big enough sphere, all the others will be at some gap. Oh, I forgot to say why it's gapped. So it's not gapless at the edge, but the point would be that this is the unique zero energy state at this angular momentum. If I tried to find another state up here, well, what these other states up here must do is have some pair that don't have relative angular momentum 3, and that will give me a finite energy cost. So numerical studies confirm, indeed, that there is a finite gap even in the limit of large electron number, at least as large as we can get. So it is an incompressible phase, but you know that if you took an incompressible liquid, it's still possible to make a little bit of you could think of it as a hydrodynamic wiggle around the edge. So in a sense, once you have an edge, then there could be gapless excitations. In fact, there have to be gapless excitations. So one ground state on the sphere, 3 ground states for the 1/3 Laughlin state. So there's still a gap. The torus doesn't have any edges. You do a numerical calculation on the torus basically just by taking the sphere with the square with periodic boundary conditions. And that object, you can do the diagonalization and 3 ground states will appear. So these are predictions that should come out of any good theory of the fractional quantum Hall effect. For today, let me just show you fractional charge. Yes?
For this analysis of interaction parameters, the function of angular momentum, you didn't mention that you have 1/3 filling. What happens if you have 1/5 filling, for example?
You mean 1/5 filling? Well, if I wanted to make a parent interaction for 1/5, I would turn up all the pseudopotentials up to 5. And then the first zero energy state will be the Laughlin state with L equal to 5, which has filling 1/5. However, there's a physics change. As you go to low enough density, there's still some interaction. Okay, so the physics assumption is that if I now return to the real world and turn these up a little bit, there's no phase transition. And that you have to do numerics to prove. But that seems to be true at 1/3 and 1/5. Once you get maybe 1/7 or below, there's sometimes an intervening phase, which is a Wigner crystal, something that is not an incompressible liquid. It's basically a rigid arrangement of the electrons. So there is no guarantee that the physical state at Coulomb interactions is adiabatically connected to the Laughlin state at model interactions. And that's true at 1/3 and 1/5. It seems experimentally, maybe not at other L. Yeah?
Putting the fractional quantum Hall state on a different manifold yields a different degeneracy. But if I take the system size to the thermodynamic limit, then they should all be the same. So
what does all be the same mean?
So if I imagine an infinite torus and an infinite sphere, so the ground state should be no.
The degeneracy doesn't have to be the same. In fact, I will give you a magic field theory that doesn't care about how big the universe is, but it does care about the topology of the universe.
So, in the real world?
In the real world, the degeneracy gets better and better as the system gets bigger. So if you took real interactions with some finite range, these 3 states would not be exactly degenerate. So if I do my 6 electrons on the torus, unless I'm very careful, there'll be some small splitting of these, but that splitting actually gets smaller as I make the system bigger. So the topological degeneracy is only kind of precise in the thermodynamic limit.
But you don't have a torus in the real world.
You mean experimentally? Yeah. Yes. That is so far the case, yes.
The 3 ground states on torus, if you take any translation invariant states, they are often standard. That's
Right, but I think about that as being fine-tuned. I mean, that's not topological. That is true if I have a symmetry that relates to 3. Yes.
Yeah, but I mean, when you say interaction,
Yeah, no, you're right. But that is true. I can definitely find... I mean, if you want a picture of why there are 3 ground states on the torus, if I take the so-called thin torus limit, it turns out that in that case, I can understand the 3 ground states through symmetry breaking. So let me take a different basis for the lowest Landau level. If I'm putting it on a long, thin cylinder, then I can make my Landau states be rings. So this would be one, this would be another. And then it turns out that there is a charge density wave. So there is a symmetry breaking. This is in general true on the finite torus, even if I wrap the cylinder around. This would be one ground state. So let's write this as 1, 0, 0, 1, 0, 0, 1, 0. So in the limit of the thin torus, this is one ground state, and the others are 0, 1, 0, 0, 1, 0, dot, dot, and 0, 0, 1, 0, 0, 1. And the magic is that as I make the torus bigger, the amplitude in this symmetry breaking goes to 0. So the charge density wave disappears, I get to 2D. But if I wanted to do it in a symmetric way, I could make this and see, in that case, these will be exactly degenerate because they are translations of each other. I think that was the comment. But the only problem with this picture is this makes it look like the degeneracy is a consequence of the charge density wave. The degeneracy remains even as the charge density wave goes to 0, which it does exponentially as the cylinder starts to have a large radius.
Excuse me?
Yes?
Do you have sphere vacuums on monopole?
Yes, that's right. There's a uniform flux out through the sphere, or a uniform flux through the torus. Okay, so fractional charge. That's the ground state. Let me make a state which slightly increases the angular momentum. So just give me some location, let's call it W in the plane. I could multiply, let's call this psi quasi-hole, is equal to the product over all the particles of Zj minus W, all multiplying psi Laughlin. So what this has done is I haven't put an electron at W, but I've said by this term that I want to keep electrons away from W. So the density is vanishing at the point W. If you want to make things simple, you could put W at the origin. In fact, let's do that, make our life easy. Well, if we put W equal to 0, then what we've done is exactly the same as what we'd get in my flux pumping picture. We've forced the m equal to 0 box to be empty. Let me justify that. Well, here I've still got this liquid. So maybe if I took the integer quantum Hall state, what we've done is very simple to state. We've just forbidden occupancy of the m equal to 0 state because once I've got product over j of z sub j, that means every z sub j occurs at least once, which means that the expansion of this over z sub j to the 0, which is the m equal to 0 state, is 0. In general, once I've got the 3 there, what I've done is rule out one of these boxes, move the thing over. But what's the charge of that operation? So we call this a quasi-hole. It's like a hole in that we've excluded an electron and moved things over. But the amount of charge we've excluded, well, if the density before was not 1 but 1/3, that is, we know the Laughlin state has average density 1/3, then there's a charge opposite the electron, so let's call it minus e over 3. If the electron is plus e, you can choose your favorite convention. Anyway, it's minus the electron charge over 3. That's my quasi-hole excitation. So that is a perfectly fine state. You could think about whether it's the exact state and so on. But that's what we mean by saying that there is fractional charge in the Laughlin state. It's not all that complicated. Fractional statistics is a little more complicated, and I will draw some pictures, and then the existence of fractional statistics will be a key ingredient of when we construct the state. So now let me show a couple of slides and try to give this Linus-Merheim argument. Yes?
Just why doesn't this work with, for example, 1 over 2?
It would work with, you mean if I had, instead of the Laughlin state, some state at 1/2? The problem is that couldn't be a state of fermions. So.
Pro of 3, you get a pro of 2, for example. You said it was an odd number. Why is that to be an odd number?
Because I want to have fermionic exchange statistics. I should get a -1 when I exchange I and J. But the state you're talking about is a perfectly fine state for bosons. In fact, if you take ultra-cold bosonic atoms and put them on a lattice, that is a state that people are trying to see. Yeah.
So does how the pseudo-potential argument work if you are on a lattice?
Actually, Andre would be a good person to ask that, or maybe someone here, like Titus. There has been work recently, so just to give background, we said a Chern insulator or a lattice Hall effect was something that had a topological band with a Chern number. If you fractionally fill up one of those bands and turn on interactions, you might hope to make something like a fractional quantum Hall state on the lattice. People have tried to develop analogs of the Landau level structure, like the magnetic translation group and things like that work on the lattice. I know several papers, but if I list the ones I know, I'm sure I'll be omitting other ones that are equally good, so you can come ask me afterward. But I know that the people at Princeton have done a lot on this, that it's possible to, in some cases, you can imitate stuff like what you're asking. You can make Landau levels work on the lattice.
And how about if you add disorder?
So the only hope, I guess, you have is that if it's gapped, a little bit of disorder shouldn't change things. But if you turn up disorder, for example, disorder can tend to favor the Wigner crystal over the incompressible liquid. The one kind of good thing about disorder, maybe from the point of view of the quantum Hall effect, is what physically happens seems to be, maybe I've got a nu equal to 1/3 state, and then some region has especially different potential or something. So in this region, maybe I get nu equal to 1 or 1/3 or something. But as long as this is a finite droplet, it doesn't really matter. So that's part of the experimental stability of quantum Hall states. Is what really matters is the percolation of one kind of quantum Hall state. If you throw in isolated droplets of other kinds, that doesn't actually matter. So this is maybe a more macroscopic picture of why it's kind of stable to disorder. But yes, maybe the classic example of this would be integer quantum Hall. Suppose I change the density in a real system with disorder, where this would be my picture close to 2 Landau levels filled. And then maybe I've decreased the density, and now I've got a little pocket of nu equal to 2 and nu equal to 1. At some point, there was kind of a percolation where nu equal to 1 started to be the one that went to the sample boundaries rather than to nu equal to 2. That's sort of like loosely a quantum version of percolation. In fact, the spirit of this is what was discussed by John Chalker at Les Houches when I was a student in '98. So I would refer you to his lecture on how to make actually a quantum model that captures this. So this is called the integer quantum Hall plateau transition. The fractional case has some of the same physics, but I don't know that we understand it as well as we do the integer case. But at least in general, if you have a gap state, you kind of expect it to have some stability to disorder. That's maybe the first answer. Okay, other questions? So I realized, as I was making this talk, something quite remarkable and depressing to me, which is that all of this happened let's see here, before many of you were born. So I thought I would give the history. Let's see here. I heard it make a noise. So let me start writing up the things we'll use for spin chains while my couple of quantum Hall slides come. Okay. So the integer quantum Hall state was found by von Klutzing et al. Theorists figured out why. I gave you the Laughlin argument, and people took that as meaning you will see these precisely quantized integers. Then fractional plateaus were found, and that was a big puzzle. And then the Laughlin argument and some generalizations give fractional quantum Hall states, but all the ones that you get by reasonable generalizations of the Laughlin state have odd denominators. So what I'm going to talk about, including the so-called abelian Chern-Simons theory I do next time, is all about this category, number 2. Adi Stern is going to come and tell you about this last category. So a quantum Hall state was found at nu equal to 5/2 Landau levels filled, and that is an even denominator. So theorists needed another explanation, and the explanation is a state that is quite different from what I talked about. So with what I talked about, one thing you notice is once I tell you where the quasi-hole is, the wave function is specified. There's no additional degeneracy or degree of freedom. The zeroth order thing that's special about this state is that once I tell you where the quasi-particles are, it's like there's a Majorana fermion living in each quasi-particle. There's an additional degeneracy. Remember, Majoranas are zero energy, and 2 Majoranas make one 2-level system. So if I've got a bunch of quasi-particles with a bunch of Majoranas, I've got several, basically 2 to the n by 2 degenerate ground states, and everything I say about abelian statistics could be more complicated. So this is what Professor Stern is going to tell you about. So why is 2D special? So in 3D, you learn something when you take quantum mechanics, but there's a hidden assumption in it, which is the following. You write down a wave function for identical particles, and the assumption that's kind of hiding in the background is what we should think about is just permutation of labels. That is, I should look at wave functions that transform simply under switching the label Z1 and the label Z2. And if you follow through with that, you get either cases where I don't get a minus sign or cases where I do get a minus sign, and those are bosons and fermions. In 2D, the key point that, as far as I know, was first noticed in '76 is the following. Let's think about how would I physically tell what the statistics of a particle are. I should move a particle around another. If I live in 3D, and here let me try to do an experiment. Let's say that this is identical to me, so that's the other particle, and we're going to try to figure out the statistics. So one path I could do experimentally to try to measure the statistics is to go around like that. Another path is to try to go around like this. So if you want, you can imagine a string tied to my head and a string tied to the identical particle's head, and that would be 2 different things. So in 3D, I can make those equivalent by climbing over the table, if you like, by lifting up one loop and flipping it over. So in 3D, the statement is that looping one particle around another in 3D by topologically lifting and twisting, counterclockwise and clockwise are the same thing. If I'm forced to live in 2D, that is not the case. So what their point in slightly more abstract language was that we should not think about statistics as representations in quantum mechanics of permuting the particles. If we're in 2D, we should think about braiding the particles. Braiding meaning you give me a bunch of particles, you flip them around each other. Adi Stern may give the precise mathematical definition of the braid group. I won't. But it's incredibly complicated. We don't even understand all the representations of the braid group. It's a mathematically much deeper object than the permutation group. The good thing is, one of the simple representations, well, we know that if we've got a non-degenerate ground state of these quasi-particles, so I've put some quasi-particles in the Laughlin state, they're almost like bosons and fermions. Since I've got just one state now, let's say, when I say ground state, I mean ground state with some particles at these particular locations. There's only one state, so when I do the exchange, I have to come back to the same state, but I might have picked up a phase. There's now no reason why that phase has to be +1 or -1. It could be something like this, e to the I theta theta for the quasi-particles in the Laughlin state is 2 pi over 3, basically 1/3 of a fermion. So, which kind of makes sense given what we said about fractional charge. So that's fractional statistics. If you're worried about why there can be an I, well, we did break time reversal by putting on the magnetic field, so that is allowed. So this would be the simplest kind of enneon. And how to make this happen with particles is one big motivation. That's how people originally developed the kind of field theory I'll talk about next time. So some experimental data you might keep in the back of your mind is that the Laughlin plateau, so the Hall plateaus are little horizontal bits in RxY that correspond to zeros of the diagonal conduction and the diagonal resistance. Remember that resistivity is a tensor. There are a lot of plateaus. There are a lot of even odd denominator plateaus, so we should try to figure out a theory that is a little bit more general than just 1/3, which is a nice big plateau. Okay, so that's all motivation, if you like, for trying to make this field theory of topological states in the next lecture. I want to give a warm-up. Let me show, whoops. Somehow I lost the one slide I wanted to show. Where did I put that? Let me show this, and I'll come back to it in a second, which is I want to explain what's different about two situations that came up of the same model. Plus, so this is the Heisenberg antiferromagnet. Actually, I think, so this is going to be motivation that the spin 1 case is surprisingly complicated. There's the pure antiferromagnet, there's AKLT, and let me come back to this other stuff maybe first thing next time so I can use the rest of the blackboard. And the figure is in my notes, and I actually have posted lecture 5 and 6 rough notes if you want to get ahead of the game and not even have to show up on Friday. Or you can show up and ask especially tough questions. Should tempt you. All right. I hope that's going to stop. Okay. So what you've learned so far is, if you paid attention, that Heisenberg antiferromagnet, the behavior probably depends very sensitively on the spin. Spin half, you can use the Lieb-Schultz-Mattis theorem it says that it should be gapless. And in fact, this was solved by Bethe when he was a 25-year-old grad student introducing the so-called Bethe ansatz. It's actually a sort of quantum critical state. It has power law correlations of the spin. In other words, if I look at the correlation function, well, it basically alternates like an antiferromagnet, but it doesn't have long-range Néel order. It goes like 1 over distance, and there is a log up here to, I'm guessing the 1/4 power, but I don't remember for sure. However, the integer spin case, well, a model very like the integer spin case was discussed by Nicolas. Let me generalize this slightly to plus alpha sum over I SI dot, guess I don't need that sum again, Sj squared. And for a particular value of alpha equal to 1/3 and spin equal to 1, this is gapped. This is the AKLT problem that he mentioned. So you might wonder, why are integer spins different from fractional spins? Well, at first you might think it's because of adding this extra term, Well, actually, it was shown by Haldane just before AKLT, so this is 83, by a quite beautiful topological argument that even if this is 0, it's still gapped in the spin 1 case, but gapless in the half-integer case. More generally, for any half-integer, this is gapless, and for any integer, it's gapped. So we want to give a quick summary of the story for why half-integer gapless, integer gap. And as a quick comment, we still have no exact solution for alpha in general. There are several exactly solvable points, which was kind of some of the stuff in that plot I flashed up and we'll come back to. But a quick comment, why 1/3? If I think about, well, SI dot SJ is SI squared plus SJ squared, sorry, other way around. SI plus SJ quantity squared minus SI squared minus SJ squared over 2. So if I think about 2 spins, then they could have total spin 0, and then I get S1 dot S2. Well, let's work it out. So spin 1 means that these are each 2h bar squared, 2h base squared, 0. If I took total spin 1, then we've got, well, 2h bar squared minus 2h bar squared minus 2h bar squared over 2, which is minus h bar squared. And then finally, 2 will have 6h bar squared minus 2h bar squared minus 2h bar squared over 2, or plus h bar squared. So if I go back and figure out what is this term, well, for s equal to 0, this is minus 2h bar squared plus 4h bar squared over 3. So I'm taking specifically alpha equal to 1/3. Okay, if I should make my spins dimensionless in order for alpha to be dimensionless. So let's just write it as minus 2 plus 4/3. S equal to 1 gives me minus 1 plus 1/3. So this is minus 2/3, minus 2/3. And then the last one will give me 2 plus 4/3. So that's something bigger, but I don't really care what it is. The point is that these two are degenerate, and this is higher, so the ground state will basically project onto spin 0 and spin 1 of every bond, and that's exactly what the AKLT wave function was written down does. Once I tune alpha away from 1/3, as far as I know, I totally lose that solution. So that's why we need something different. Okay. So we need to make a field theory for quantum spins. And this is a technology that the answer is pretty easy to state and kind of intuitive. But when you think about it at first, it sounds hard because we want to make a path integral, which is usually an integral over classical trajectories. What is the classical trajectory of a spin half, say, or a spin 1? So for spin, the answer is to make a representation where indeed spin winds up looking like a classical unit vector. And the way we do that, to be precise, is so-called the coherent state representation spin s. So I make a continuously variable set of states. Let's call them omega hat, labeled by a unit vector, omega. Now, this is continuously variable, so that's an uncountable set to span a 2s plus 1 dimensional space, so it's very overcomplete. Which we don't normally like in quantum mechanics, but in this case it's kind of a necessary evil. In fact, there's no way to make a rotationally symmetric parametrization of, say, spin half. You pick an axis and then you've got up and down, say. But you can make an infinite dimensional rotational symmetric version of it, which is these coherent states. And the good news, which I'm not really going to derive, I did derive it in my notes, and even better, the book by Auerbach that I saw on the desk in the library has a very explicit derivation of this. I find it a little bit clearer than the original paper. I'm going to tell you the theory you get is actually a very famous kind of theory and good to know even from the classical stat-mech point of view, plus a simple topological term. So the theory is of the form nonlinear sigma model, which I'm going to define, plus the simplest kind of topological term. Which comes from the spin-Berry phase that we've already talked about, actually. So there is a derivation that's worth reading, I think, if you work in quantum magnetism, of how you get this. But let me tell you, what is this nonlinear sigma model? Because it's probably the second most important kind of field theory after Ginzburg-Landau theories in condensed matter. And you can think of it as trying to describe the low temperature limit of Ginzburg-Landau. So you probably know Ginzburg-Landau theories, well, or even just think about Ginzburg-Landau equations for superconductivity. That's a theory in terms of an order parameter. So nonlinear sigma model is an unnecessarily complicated name coming from particle physics. It's basically trying to do Ginzburg-Landau at low energy, where we might expect that magnitude fluctuations are expensive. And let me draw a picture to try to illustrate that. Okay, so let's think about XY symmetry breaking, because that is the simplest example to draw. If we do the mean field energy as a function of, now we've got a two-component order parameter. So my axes will be something like phi y, phi x, and energy, then, well, if we just looked along the x direction, it would look kind of like the Ising model. And I just need to rotate this around the z-axis. So let me just draw how the minimum of energy, this is sometimes called a Mexican hat potential, it sort of looks like a sombrero. If you look at the minimum of energy, it's a circle. This is what we called the order parameter manifold before. The order parameter manifold is the set of inequivalent ordered states once I'm in the ordered phase. And the point is the following. It's really not necessary to treat these two kinds of fluctuations the same way. So I could either fluctuate along the circle, which is the degenerate ground states related by the broken symmetry, or I could fluctuate in this hard direction. And fluctuating in the hard direction is going to cost me a lot of energy. If I'm at low temperature, it'll cost me more than the thermal energy, so maybe I should just throw that out and think about trying to define a field theory that instead of living with a two-component order parameter now the field is just being somewhere on the circle. So we could write down, and this is exactly the same field theory of the height model that was in Professor Chalker's lectures. Something like, if we were just motivated by StatMech and not even thinking about quantum spins, we would write Z is equal to some path integral. And let me label the angle around this circle of ordered states, d theta. And now let me get my notation right. E, if it's a StatMech path integral, we should put in a 1 over temperature, that's beta. Some coupling constant, I don't know. And then d theta squared over 2 d dx. And the cases we've been talking about, and I will be talking about, let's say we're in 2 dimensions. So if I remember that theta is an angle, this is a theory that's already kind of interesting. It has a Kosterlitz-Thouless transition because theta is compact, which allows vortices. If theta were non-compact, if it were just a real number, then this is just the Gaussian field theory, and it always has power law correlations. So that's the statement that except for fact that theta is an element of S1 instead of R, this would be a free theory with no phase transition. That's not true. So this would actually be kind of like a linear sigma model. It wouldn't have interactions except for the vortex. Once we go to more complicated kinds of order, like, for example, you probably have heard that the XY model of classical spins has a phase transition at finite temperature. We know that the Heisenberg model does not in 2 dimensions. And now I'm talking just classical Heisenberg spins. Indeed, I'm not going to try to prove that to you, but I think you've probably heard that the XY model is special. It has no long-range order at finite temperature, but it still has this unusual BKT phase transition. Heisenberg model doesn't have any of that. It's always short-ranged. So that's a clue that if I made this instead d n hat, e to the minus beta c gradient n hat squared over 2 d2x. So this would be a nonlinear sigma model. If we wanted to use fancy notation, we'd say this is from the plane R2 to the sphere S2, where that was to the sphere S, that was to the circle S1. This model is always disordered. Now, going back to quantum spin chains in 1D, we kind of expect a quantum model at 0 temperature. So if I think about a path integral for a particle, in quantum mechanics, that becomes an integral over time. If it's the partition function, it's imaginary time, but there's an extra dimension. So when we do 0 temperature quantum physics, we expect to add an extra dimension in our path integrals. So the point of Haldane's mapping for the spin 1 antiferromagnet or for any, actually, spin S antiferromagnet, and this actually is more complicated, but the end result is very plausible. Well, we'd expect to get a field theory now that involves dx and dt, but the first term is exactly this nonlinear sigma model. So the way to think about this n now, so instead of d squared x, I should think about dx d tau. So it's an imaginary time path integral for a quantum system. If that sounds bizarre, you can learn more in the book by Auerbach, for example, or maybe, I don't think I explained that in the notes. I mean, I did derive it, so even if you never seen an imaginary time path integral, I think you can derive this fact. It just takes a bit of work. This n you should just think of as the local antiferromagnetic order. So I've kind of taken out the staggering in order to coarse grain. N is some smooth field of space and time. So the end result after that is that the quantum system has a path integral that is almost this nonlinear sigma model we could understand classically. Let me write it this way. So it's an integral over trajectories of this vector in two-dimensional space-time times a Berry phase term that I'm going to justify for you, and then an e to the minus integral dx d tau of the nonlinear sigma model into S2. So in other words, if you just had no better knowledge than the fact that this should be a 1 plus 1 dimensional quantum problem, that is one spatial dimension, one imaginary time dimension, and it should have something like a vectorial order, because we're talking about vector spins, you would write down the nonlinear sigma model. There's an extra term, which is just the sum of the Berry phases, basically. It comes from the sum of the Berry phases of all the spins. So the one reason why I'd suggest that maybe you should look through the coherent state path integral when developing the spin path integral, the only interesting thing that happens is there is a Berry phase term. So even just for one spin, there's a term that I wind up with, which is of the form e to the 2 pi I times the spin, times, now I've got an integral that I can write as the area traced out. Actually, sorry, I don't need the 2 pi here. By the spin trajectory on the sphere. So an example that both came up in something I said earlier and also something Professor Levitov said is that if you take a spin in a Zeeman field and change the Zeeman field adiabatically, there's a Berry phase that builds up, which is related to, as my spin traced out some path on the sphere, what is the area enclosed by that sphere? Well, enclosed by that path. Let me maybe give you an argument for the coefficient there. Well, so the meaning of this term, what I mean by the area traced out by the spin, so I've got some path integral for a stat-mech partition function, which means I have closed paths of the spin. And if I do, say, this path, well, I could think about that either as enclosing this lower part of the sphere or as enclosing the upper part of the sphere. But you can check that you will get the same answer however you define the area. So if you like, it traces one way around the bottom of the sphere, or it should be physically equivalent if I trace the other way around the top of the sphere. And indeed, that's true. So now, finally, we can see that this depends on the spin. And Holding's point from this path integral was that this term gives me a very basic difference once I have all my spins in my one-dimensional chain. So n is a function of x and tau. This term is actually exactly the topological thing I wrote down before. This Berry phase, we understand its effect in one dimension, that's what I'm going to tell you. People are still a little bit not always clear on what it does in higher dimensions, but we can write it as 2 pi times the spin times something I'll call big theta, where theta is a function of the spin configuration, n of x tau, and theta, to be precise, is something I wrote down before, It's the topological integer that counts. I've got a mapping from R2 to S2 given by the field configuration n hat. That traces out some pattern on the sphere. Now I've got a two-dimensional pattern dx d tau, and this is an integer. It actually just computes pi 2 of S2 for that map. That is, we know pi 2 of S2 is z, and this is normalized to give me that integer for the particular configuration. So finally, this is what I mean by a topological term in field theory. I haven't really defined it yet, but a topological term in field theory is something that gives me a topological number, topological invariant, for every configuration. We still have a path integral, which means we have a sum over configurations. But Haldane's point now is easy to state if we look at 2 pi times s times an integer, which is that if s is integer, then this Berry phase term does absolutely nothing, because it's always plus 1. That is e to the I. Is that upsilon, I guess? Is plus 1. While if s is half integer, then this is plus or minus 1 depending on the configuration. So if you like, integer spins in this approach are kind of the easier ones, because then we just get the nonlinear sigma model, which is just like the 2D classical Heisenberg model and flows to disorder. It has a gap. It has a finite correlation length, in other words. Although that correlation length is very long, for s equal to 1, that is, the correlation length is the length scale on which the correlations fall off. This is 6 or 7. By the time I get to s equal to 3, this correlation length is about 1,000 spins, which means the gap in energy is really tiny, and this would be quite hard, not absolutely impossible in the days of DMRG, but it was certainly impossible when Haldane wrote the paper. There is a tiny gap even for spin 3. I don't know if people have gone higher than that. While half-integer spin, there's at least this topological term that doesn't really tell you how to solve it, but fortunately, Betha gave the exact solution for the spin half case, and Shankar is one person who wrote a paper kind of explaining why this term has the effect of keeping it gapless. But at least what you can see from Haldane's Berry phase term is that there is some difference between integer and half-integer. So that's the first kind of topological term in spin chains I wanted to discuss. Let me maybe show that slide as motivation for where we start next time and explain a couple of things on it. So if you like, AKLT is the exact solution of the approximate problem. What Haldane did is the approximate solution of the exact problem, but they are in fact the same phase. So for example, this will have the same edge states that Nicolas Regnault talked about. So let me flash this up, and then there'll be one last puzzle about spin chains that is resolved by a slightly different topological term. And then we will get on with Chern-Simons theory. And I realize that if you've never seen field theory, for example, before, this may be a bit complicated, but please do look. I'm hoping that the notes are up. If not, I'm sure they will be soon. I've already sent them in. So this is the full phase diagram of the chain of spin 1 with both bilinear and biquadratic interactions. All that matters, so this is all about the ground state. All that matters for the ground state is the ratio of this term to that term, which is often drawn as an angle. So the Haldane point is what I'm calling theta equal to 0. So that's the pure bilinear model. AKLT point is a little bit up here, so I put AKLT. This figure is from a nice numerical study by these folks. So the Haldane phase with the gap and with these edge states extends over some finite region. In fact, in hindsight, this is maybe the first example of symmetry-protected topological order in an interacting system. Hopefully someone else at the school will talk about that. I think Frank Pullman will probably talk about that if no one else does. And then there are transitions out of that point. So this is one quantum critical point. This is another quantum critical point. These are actually different from each other. and they're also different from the criticality of the spin-half model. So this label, it's a combination of a symmetry group, a Lie group, SUN, either 2 or 3, and then a little subscript, which is something called the level, and I want to explain what this means and what the field theories are for these gapless points. So to be precise, to actually solve these, so I think this one was Uyman, Lai, and Sutherland, and this one was Babujian and Takhtajan, sometimes called the Armenian point. This, I can at least tell you what the critical theories are for these points, because that's another cute application. Like basically here we used pi2 of S2 being Z. In order to explain what these are, we can do that in 10 minutes or so. We just need to explain, we need to use the fact that pi2 of these Lie groups is 0 and pi3 is Z. And we're going to write down a different topological term, which is called a Wess-Zumino term. And these two critical theories are called Wess-Zumino-Witten points. It's maybe the simplest example of a one-dimensional critical point with Lie group symmetry beyond the Heisenberg case that we already talked about. So it's one more nice topological term, and then we will go back and construct something that's not just a topological term, but a topological field theory. So again, to make the difference, topological term means I've got some ordinary Maxwell or nonlinear sigma model or Ginzburg-Landau, some ordinary theory like that, and I'm adding something that is a bit topological. To be precise, in this case, it integrated to a topological invariant. Something very similar to that, not exactly the same, is what happens with this other term we're going to write down. So I'm only going to talk about this region of the phase diagram, but that's the most physical. And then a purely topological theory, if you want to struggle with something for the next couple of days, a purely topological theory can only depend on the topology of space-time. It can't depend on the metric. In particular, there's no notion of finite energy. So a purely topological field theory has to be a very strange object. It can have zero energy states, and it can have infinite energy states, basically, but that's all. So how can that be? Well, on the bright side, that means that it must be a fairly simple theory if we can solve it, and the magic is we can, so we can exactly solve the Chern-Simons theory I'm going to talk about. Even though it looks like some complicated 2+1 dimensional gauge theory, it's actually a much simpler theory in disguise, and that mystery we will resolve on the next lecture. Yes?
Those are conformal field theories.
That's right. No, yeah, then the Chern-Simons is different from these are Wess-Zumino. No, sorry. We're going to finish spin chains and then do a fully topological. So these are coming from topological terms added to a nonlinear sigma model. Then we move on to fully topological theories, just trying to explain the difference. Good. So, questions? Otherwise? Yes? Oh, sorry, this is squared. I typo. Yes, sorry, that should be a 2, not a 3. I don't know what happens with the... I think with the 3, it has to be trivial for spin 1. So it's, or it has to be precise, it has to project onto that probably. So, good. 2.
What's the symmetry that protects the Heisenberg phase?
Well, it's gapped, so it doesn't actually need to be... Okay, I see what you mean. You mean, I said it was symmetry protected. It turns out I believe it's inversion symmetry. So what I mean by that is the Haldane phase, for example, you heard that it has these edge states. It has spin halves at the edge. I could imagine adding a term. So this would be trivial for spin half, but it's not for spin 1. Add an on-site one-axis anisotropy. If I crank this up, I'll get a trivial phase, which is SE equal to 0 on every site. So that doesn't have any interesting tail states or anything. So the question you can ask is, does a phase transition happen necessarily between the Haldane state and this? I have not worked on this myself, but my understanding is that if you keep inversion symmetry, there has to be a phase transition, and if you don't, there doesn't have to be a phase transition, and that one way to understand that is through the entanglement spectrum that Nicola talked about. But if I said anything wrong, please do correct me. I won't be embarrassed. No, it sounded okay? Okay, good. So,
I think there's more symmetry technique, and 3 kinds of symmetries, and if either of them is there, then it's different technique.
okay,
I don't remember the
there you go. So it can be other symmetries than inversion as well. But at least inversion is sufficient. I know that. Good. Other questions? Okay, then.